In this video, I will go over another example of using the method of separation of variables in Cartesian coordinates. The goal will be to solve again for Laplace's equation where the Laplacian of the potential is 0. The system that I have here, this is the 0 of the coordinate system, and this is the x-axis, this is the y-axis. My system is three-dimensional, so it is extending along the z direction. Now, if you take a cross-section on the xy plane, what you will see is a constant potential here at v0, a constant potential here at v0, zero potential here, and zero potential there. But the system does extend in 3 dimensions on the z-axis as well. So, since the system though is the same along the z-axis, then there is no need to do separation of variables using a z function. I know that the potential really will depend on x and y, not on z. So I set the potential to be the uppercase x that depends on x only, and uppercase y depends on y only. And then using this in Laplace's equation, you obtain the two ordinary differential equations, the same as the ones we've seen in the past. Now, in the y direction, I know that the boundary condition when y, so these are going to be my boundary conditions. When y equals 0, I know that the potential there needs to be a 0. And when y equals a, similarly, I know that the potential needs to be at 0. Now, as I've said before, when you see that you have your potential needs to be 0 at two different places along the same direction, this is an indication that you need to have a negative constant here. So I will write this as minus k squared y, and this means that the solution for this function will be there will be sinusoidal solution, so it will be a sine ky plus b cosine ky. Now, for along the x-axis, the boundary conditions that I have, when x is minus b, my potential is a constant, and when x equals b, the potential is also a constant. Okay, these are the boundary conditions, and I think I've said this before. These are extremely important, and whatever solution you find, that solution needs to obey the boundary conditions, and these boundary conditions really determine your potential where you're trying to find it. Now, along the x-axis, it is a little bit more not so easy to decide whether you're gonna use the sine as your sinusoidal functions as your solutions to the differential equation or exponentials. But at the end of the day, the important thing is to be able to impose the boundary conditions in your solution. And if you can do that, then you have found the only solution that exists. Now, here, let's try using the exponentials as we did in the other example. So it will be c e to the kx plus d e to the minus kx. And now we have to start looking into imposing the boundary conditions. We can start the first one, the easiest one to impose on our solution will be when y equals 0, the potential needs to be 0. And when I use, let's say boundary conditions, this is 1. And let's make this 5 and 6. All right, now using 1 and 6, when I plug in y equals 0, the first term goes to 0, so I don't really obtain any information about a. But when I plug in y equals 0, I have cosine of 0, 1. The y function becomes just b, but I know the potential there needs to be 0. This means that b is 0. Now, let's get rid of this. Now, I have a sine ky, and the next boundary condition that I can easily impose is using the second one, equation 2 and equation 6 again, but using only the first term. The potential needs to be 0. This means that 0 equals a times the sine of k a, because y equals a, according to boundary condition 2. And now the only way to make this happen is if the sine is 0, and we have seen this before. This is only possible if k is n times pi over a, where n takes the value of 1 or 2 or 3 all the way to infinity. So this second boundary condition gave me k, and now I can move on and see how to impose the boundary conditions on 3 and 4 on equation 5. Now I will use both 3 and 4 on equation 5, and what this will give me, I will start writing here, c to the e kb plus d to the e minus kb should be equal to v naught, and that should also be equal to c e of minus kb. And now, so on the left side, I'm using the value of x, b as the value of x. On my right side, I'm using minus b for the value of x. And those two values, the left side and the right side, they need to be equal because they are both equal to v naught plus d e to the kb. Now, looking at this, the conclusion is that the constant c needs to be equal to the constant d. And this makes sense because if you look at the figure, the system is entirely symmetric along the x-axis. You have minus b, and it's the same potential. So the solution needs to be symmetric since the system is symmetric. And now combining everything, let's call this equation 7. This is equation 8, and then 9. What I have left for my solution is a sine ky, and k is n times pi times y over a, and then I have c ekx plus c e to the minus kx. I can take the constant c out, and I can really merge it with the constant a. The important thing is that you have a constant. It doesn't really matter whether you say e to the kx plus e to the minus kx, but let's write k as n pi over a, this is x, plus e to the minus, nope, there is no minus, plus n pi a, this is a plus. All right, and now as I mentioned before, the n can take values 1, 2, 3 all the way to infinity, and this means that this is a specific solution, and I can write the general solution to Laplace's equation by adding an infinite number of these specific solutions and making the constant a specific to that term. So my general solution will be where n equals 1 and it goes all the way to infinity. And to make my life a little bit easier, I will rewrite this as the sum of n goes from 1 to infinity, a, the constant a sub n. Remember, the constant a depends on what n is. You will have a different constant for every term. The sine of n pi y over a. Now, the sum of these two exponentials can be, okay, instead of writing the sum of these two, you can also write the hyperbolic cosine. And now I still need to impose the boundary condition that the potential when x is b, the potential is equal to v naught. And remember, I already took into account the symmetry of the problem here when I set the constant c equal to d. So once I say that when x equals b, the potential is equal to v naught, because I took the symmetry into account, I'm done. So the last thing I need to do is apply, let's call this equation 10, apply boundary condition 4 on my general solution. So when x equals b, I have b comma y is equal to, this needs to be equal to v naught, and this is the sum a n sine n pi y over a times the hyperbolic cosine of n pi b over a. And I can use Fourier's trick to solve for that for the coefficients a sub n, and this 1 over the hyperbolic cosine term so this is 1 over that, and then we have 2 over a, the integral from 0 to a, the constant v naught times the sine of n pi y over a dy. So this is, now let's call this equation 11. The solution to the problem is the following. This is the expression that gives me the potential as a function of x and y, and the coefficients a sub n are given by this expression over here, expression 11. And the fact that the coefficients a are given by this equation for in order to for the potential to be equal to v naught when x equals b and when x equals minus b.